All right, and here we go. In order to form an electric circuit, what do you have to have? Yeah, all the above, right? So you need a closed circuit, some kind of voltage source. You need a resistor on your circuit. You need all those things. All right, points on the board. In order for current to flow in a circuit, yeah, so a complete path for the circuit, that's also called a closed circuit, right? An open circuit, like if you hit the off switch, that would like break open the circuit and the current can't flow. Right? Okay, so you need a complete path for from the voltage source through the resistor back to the voltage source, right? And that would be a closed circuit. Electrical resistance is measured in ohms, right? Okay, so joules measures energy or work. Volts measures, you could call it voltage, you could call it potential difference for volts, right? Amps, what does amps measure? Current, right? But resistance is ohms, right? Isn't it? I think it's one of these posters up here hanging from the ceiling. All right. A closed circuit is a circuit in which charge, closed circuit. Yeah, can flow. So like all the circuits that you guys have been doing on that circuit page, those are all closed circuits. Right? If it's open, then all the light bulbs turn off because the current can't flow around. Okay? Yeah, you need a closed circuit. Guys remember this when you're back in the lab area with those Christmas lights, right? If you like broke the wires away from each other, all the bulbs turned off. When two bulbs are connected in series, what's true? All right, yes, it's the same current that flows through each bulb, regardless of what the resistances are. Bring up Kirchhoff's rules again. So we're talking about this one right here, series. You guys remember this right here? The current's the same everywhere. Okay. Now, they could be like 1 ohm here and 99 ohms here. It doesn't matter, it's the same current. Okay. So I've been using two main analogies for current. One is like flow rate of water, right? Like gallons per minute. It would be the same gallons per minute everywhere. Right? You might have varying pipe sizes, so still concentration of flow. The other analogy I've been using for this is traffic flow, right? Say you got from this point to this point, right? This node to this node, say like 100 cars flow across, right? Maybe there's a bunch of stop signs here and a different number of stop signs here. Same 100 cars have to go through all of them. It does like the same number of amps everywhere. Yeah, same current. The symbol to represent resistance yeah, zigzag line represents a resistor, right? Now, two straight lines, if they're the same size, that's a capacitor. If they're different lengths, that could be a voltage source. But yeah, zigzag line, there's your resistor right there. When resistors are put in series, what happens to the overall resistance? Yeah, you guys see like this poster right here, resistors in series, you just add up the resistances, right? So if it's like 5 ohms and 10 ohms, you say 5 plus 10 is 15 ohms, right? So the resistance goes up for resistors in series. When resistors are put in parallel, what happens to the overall resistance? Yep, exactly. Yeah, it gets smaller. right? So if you have two resistors specifically in parallel, you can use product over sum. If you have more than that, you can use that fraction method you guys see up there on that poster. The story I've been using that goes along the exact same math is like painting a fence, right? So the more people painting a fence, the less time it takes to get the job done. Yeah, so there you go. Smaller time to paint the fence, smaller resistance overall, resistors in parallel. As more lamps are put into a series circuit, what happens to the current? Yeah, it does decrease. Okay, now here you have to put a couple of ideas together. You guys just said more and more in series will increase the resistance. Then kick over to Ohm's law, says that the current is equal to V divided by R. So if there's more resistance, there's less current. And you guys remember this too, because when you were back in the lab area, string up those Christmas lights, you guys remember the more you put in series, the dimmer the bulbs got? That might be an indication also that there's less current flowing, right? When more lamps or resistors are put in parallel, what happens to the overall current in parallel? Does increase. Yeah, you guys remember every time you added on another bulb in parallel, they just maintain their brightness, right? Okay, so then the voltage source must have been just pumping out more and more current every time you tag on another bulb in parallel, right? Or the other way, of course, you could think of this is that more bulbs in parallel, the resistance goes down, kick over to Ohm's law, less resistance is more current. However you get to it, it's the same answer. Right? The current will increase. Compared to resistance of two resistors in series, the same two resistors in parallel yeah, all right, we just kind of do this, right? So say you have two resistors that are each 10 ohms, 10 ohms and 10 ohms. If you put them in series, 10 plus 10 makes 20. But if you put them in parallel, what would 10 and 10 in parallel be? How about this? If it takes one guy 10 hours to paint a fence and his friend also 10 hours to paint a fence and they team up and make a two-man team, should it take them about 5 hours to paint that fence, right? Or if you do product over sum, see 10 times 10 over 10 plus 10, that's 100 divided by 20. Oh, that's 5, right? See how the resistance is going down for parallel, right? When one bulb in a series circuit containing several bulbs burns out, opens the circuit, and what happens? Yeah, none of the other bulbs will light up. Okay, let me flip over and this one on paper. All right, so see this one, right? If you guys are looking for patterns, you might have a pretty good guess what the next question is going to be. So let's do this. Let's put 3 bulbs in series. That would be 3 bulbs in series, right? Is it? And let's say this guy burns out. Wouldn't that effectively open the circuit and now the electricity can't even flow? If the electricity can't flow because the circuit's open, then none of the bulbs are going to light. That's the answer to the one we just did. Okay. Now, what if you had bulbs in parallel? See what that would look like. That'd be 3 bulbs in parallel, wouldn't it? Right? Now the current has to go through like some bulb. There's no short circuit here, but what if this guy burns out? The current could still have a couple of pathways to go through. So wouldn't the other 2 still light up? Right? In fact, their brightness would not change at all, right? Because this voltage difference is the same, resistance is the same, Ohm's law, I equals V over R. Right? I remember I don't know if this might still be true, but I remember back in the day there were different brands of Christmas lights, and some Christmas lights were wired in series, and if one went out, it's like the entire string didn't work until you replaced the bulb. And other manufacturers wired them in parallel, so if one bulb went out, the others just stayed on. Yeah, so different ways you can wire up Christmas lights, right? Different effects. Here you go. One bulb in a parallel circuit burns out. What happens to the other bulbs? Yep, burn the same as before. Same as before. Right. So if you pick the red one, that's just for series, and then for parallel, yep, I'll burn the same. Okay. In a simple parallel circuit, oh, one winner, one winner. Ho, ho, ho. So the current could totally be different. The only case where the current would be the same is if they were all the same resistance. But that doesn't have to be it. But the voltage drop does have to be the same, and I'll show you guys why. Let me flip over. All right. Share, flip over. So we're talking about parallel, right? Parallel. Okay. That's like, okay, from this node to this node. Now the current will split, and the current's probably going to be different again, unless they're like with the same number of ohms. But if they're different number of ohms, then more current is going to travel along the path with less resistance, right? But the voltage drop has to be the same. This right here actually is the answer to the question you guys just got. There's a reason I've been having you guys draw these waterfall models so you can get a different visualization of this. Okay? So look at these resistors in parallel. These are all in parallel, right? Right. See how I'm just going from the pink plane to the green plane, right? And each color represents a certain elevation, right? They all have the same elevation change. All these waterfalls are the same height. Now, I might have a big fat waterfall here that represents a large number of amps of current, right? Which I do because I have a very small resistor. This guy has 4 amps of current going through it. Versus my 2 skinny waterfalls, well, that's because they're huge resistances, right? 12 ohms, so I've only got 1 amp going through each of those, right? But they're all the same voltage drop, right? They're all like 12 volts, right? Is that? And that's Kirchhoff's loop rule. Up 12 volts, down 12 volts. Up 12, down 12. Up 12, down 12. Okay, guys get that? And the simple parallel circuit yeah, all those statements are true. Yeah, all the above. Right, so current splits, more current goes through the less resistance. That's what the red one says. Okay. Okay, so if the current divvies at the branch, right? So if you have 10 amps coming in, maybe it splits like 3 amps versus 7 amps. Right? But the voltage drop is the same. We just talked about that one. Yeah, all the above. Oh, fuses and circuit breakers are used to what? Yeah, those are all true statements. Prevent overloading, break the circuit when there's too much current flowing through, and protect us, right? So if you plug in something, you draw in too many amps, right? Fuse will break or the circuit breaker will switch, right? And it will cut the current. Right? A short circuit. Ooh, talk about this. Okay, here's what we're looking for. The positive is connected directly to the negative. Now that would be a true short circuit. The example I've been using for this is if you unwind a paperclip and touch the positive end of the battery directly to the negative end of the battery, right? There's like almost no resistance. And so the battery gets, the wire gets hot really fast, the battery drains really fast. That'd be a short circuit. Now, realistically, you do want like some resistance on your circuit, right? You want a resistor, and a short circuit would not have one of those. The other context you guys sort of saw this is one of the circuits I didn't put a short in it. Now, it wasn't a complete short circuit. There were some resistors that the current had to go through, but some of the resistors were shorted out, right? So short is like when you, have like zero resistance at some point, or in this case, maybe the whole circuit, right? All right. Short circuit. Two lamps, thick filament and thin filament connected in series. What's true about the current? Oh, no winners. Flip over here. Let's take a look at this. All right, so I know you may have been thinking of this because this does have something to do with not just this question. There's a few questions, something about thick filament versus thin filament. So think about this one more time. You guys know if it's a thick filament, that's a huge cross-sectional area and a very small resistance. If it's a thin filament, that's a very small area and very large resistance. Okay, so we're talking about different numbers of ohms, right? I mean, maybe that question could have been phrased like two resistors at different resistances. Now, it did say series, right? It said series, it said what's going on with the current. And this right here is the answer. This is the answer to that question. Okay? Is that if all your resistors are in series, it doesn't matter if they're thick filament, thin filament, large ohms, small number of ohms. The current's the same everywhere. It's a one-way street for all the amps to travel on. Okay, that'd be true. Okay. Actually, let's get a good look at this page because I bet there's 3 more questions coming up that might involve this and this and this. Do you guys think? Right? So staying in series, you guys see the voltage is going to drop a little bit proportional to each one. That might have something to do with the thick filament, thin filament. There might actually be a difference there in that case. If you're in parallel, see, thick filament, thin filament, doesn't matter for voltage. Voltage drops the same either way, right? But the current would split, and probably more current would go along the thick filament, I'm thinking, right? Give you guys a little preview, some questions about to come up. Two lamps, thick filament, thin filament, connected in parallel. The voltage drop is greater across the lamp with the what? One winner, same voltage drop. There. Let me point out to you guys exactly what I just showed you. Right, so parallel, right? Maybe these resistors are different, right? Different ohms, thick filament, thin filament. The voltage drop is the same regardless, right? That's also consistent with this last waterfall model, right? Maybe, different resistors, but they all have the same voltage drop because they're in parallel, right? All same height waterfall. You guys remember this? Two lamps, thick filament, thin filament, connected in parallel. The current is larger in which lamp? Yeah, the one with the thick filament, because that has less resistance, right? More cross-sectional area, less resistance. Okay, guys remember that formula? Right. Do a similar lab to that tomorrow. Right? Less resistance, more current's going to cut that way. Yeah. Right, and then for completion, two lamps, thick filament, thin filament, connected in series. The voltage drop is greater across which lamp? Oh, one winner. All right. Let's flip over and look at what that is and why. All right, so this right here is the question you guys just got. Right, well, that sort of combined with this. So let's put two and two together. Right, so it said series. Right, you guys know the current's the same everywhere, but the voltage drops a little bit. Let's go waterfall model for that again. All right, here's straight series setup. Right, drops a little bit. But these waterfalls are all different heights. Right, now they have to add up to the battery, but they're all different heights themselves. Right, and in fact, there's a greater voltage drop for a greater resistor, right? The greater the resistor, the more the voltage drop, right? But then how do you get a greater resistor in terms of like thick or thin filament? Well, remember, if it's a thick filament, that's a small resistance, therefore a small voltage drop. If it's a thin filament, that would create a great resistance, a huge resistance, and you get a greater voltage drop. Right? Put it all together. $70-watt bulb connected to a 12-volt car battery. When another 70-watt bulb is connected in parallel, what happens to the battery's output energy? Parallel. All right. So if you pick the blue one, you probably were thinking series, but because it's parallel, the answer is wrong. It's going to double. You guys remember back in your lab, every time you added on another bulb in parallel, they all maintain their brightness, right? So that's what happened here. So not only does the battery have to supply the 170 watt, it also has to supply the other 70 watt, also at 70 watts, right? So yeah, that would double the current and therefore the energy leaving from the battery. The total resistance of 9 ohms and 10 ohms in series is what? $19. Yeah, 10 plus 9. There you go. Just add them up. Add them up. Add them up. 10 plus 9, 19. How about 4 ohms and 4 ohms in parallel? What's that? All right, 2 ohms. Actually, that's the only possibly true answer because in parallel, doesn't the resistance have to go down? Right. So to get the exact answer, you could do product over sum. 4 times 4 is 16. 4 plus 4 is 8. 16 divided by 8, that's product over sum. 16 over 8 is 2 ohms, right? Or how about this? Let's do painting a fence analogy because working in parallel, painting a fence. So it takes one guy 4 hours to paint a fence, takes his friend 4 hours to paint a fence. Now they're going to make a 2-man team. Shouldn't it take them 2 hours to paint that fence? Yeah, it's the same math, right? Same math. The current going through 2 identical bulbs connected in series is 1 amp. The voltage across both is 140 volts. What's the resistance of a single bulb? Okay, 70 ohms. Let me switch over and show you guys why. Share. Here. Actually, I've got this one worked out ahead of time, so let me just show you this. Okay. So now they said 2 bulbs in series, right? Here's 2 bulbs in series. So the schematic diagram, a bulb could be a resistor, like still zigzag, right? Do some bulbs above it, just to point out. Okay. They said 1 amp is flowing through. They said there's a potential difference of 140 volts across the whole thing. Now, because the bulbs are identical, that means the same resistance. Shouldn't it drop 70 volts followed by another 70 volts? Right, so you guys got 2 waterfalls in succession, one after another, both like 70 volts tall. Right. Then what was the question was what's the resistance? Or wait, what's the resistance? Right, I think it was right. So Ohm's law, I equals V over R, or you could rearrange that and get V equals IR. Now, if you got a 70-volt drop per bulb, and there's 1 amp going through, then wouldn't the resistance of each one be 70 ohms, right? Yeah, so that's how those bulbs are actually manufactured, to have filaments that have 70 ohm resistance. Oh, true, false time. In order to make a flashlight light up, all you need to do is run a wire from the positive terminal of the battery to the center of the bulb's base. Will that make the bulb light? Good call, false. Okay. I do want to draw this one out for you guys anyway. Yeah, one person picked true, but the correct answer, of course, was false. Okay. So if you did that, here's what we have. We got a battery, like a voltage source, right? And then over here, you got your light bulb. Okay, here's positive terminal of the battery to the bulb, and then is that bulb gonna light? No, because that's an open circuit, right? Nothing's lighting there. The way to make it light, you got to take the wire all the way back to the negative terminal of the battery, and that's what was missing. Okay, but most of you guys got that, so good deal. When bulbs are connected in series, they all carry the same current regardless of their resistances. True or false? Yeah, that's true. Connected in series. Here, let me show you guys that again. Okay, so connected in series, yeah, it's the same current everywhere. You guys remember this right here? That's the answer to that question. Series, one-way straight, the same number of amps go everywhere, right? Regardless of the resistances, right? Same number of amps. In a series circuit, the total voltage drop across a series of resistors is the sum of the voltage drops across each individual resistor. True or false? Yeah, true. Here. Guys, a couple of perspectives on this. Well, okay. This is where, like, if this was like 3 ohms and 7 ohms, so you got 100 volt drop from here to here. It might drop 30 volts and 70 volts, but those have to add up to 100 volts, right? Okay. Or how about this, the waterfall model? Let's look at the series example. The first one was just straight series, wasn't it? Right. So do you guys see how I've got a 12-volt battery? And then this waterfall, I got 6 volts. This one's 4 volts tall, and this one's 2 volts tall. But 6 plus 4 plus 2 adds up to the 12, right? So yeah, as long as you have a series setup, the voltage drops should add up like that. That is called Kirchhoff's loop rule. Kirchhoff's loop rule. In a parallel circuit, the current in each branch is the same. True or false? Okay, got 50-50. Okay. Let me show you guys why this is the case. Why that would be false. Okay. All right, so here's let me zoom out here. There you go. Okay. Here's a parallel setup. You guys remember parallel? The current has to split, right? Okay. No, the voltage will be the same across each one, but the current splits, and more current wants to go through the path of least resistance, right? You guys remember that? The only way it would be the same is if they were the same resistance, but that's not generally true. A schematic diagram is a simplified blocked out picture of a circuit in which parts of the circuit are represented by symbols. Yeah, true. Right. We're doing lots of schematic diagrams. True story. When resistors are arranged in parallel, their overall resistance is less than that of the smallest resistor. Is that true? Yeah, that is true. Okay, so you guys see resistors in parallel here up here on this this poster. Remember the story I keep using for that? It's like a team of people painting a fence. What if it takes one guy an hour to paint a fence? And then he teams up with somebody who it would take him like 10 hours to paint the fence. If they make a two-person team, can they still do the job faster than the fast guy alone? Yeah, they should be able to knock out that job faster than an hour, right? So if you have 1 ohm and 10 ohms in parallel, the overall resistance is less than 1 ohm, right? Product over sum. That is true statements. In order to prevent overloading in a circuit, fuses are inserted. Kind of got this question earlier. Yeah, true. But you know, the question that I like more than the, I'm gonna give you guys a lead into this last question. It's also about fuses, but it's actually the more critical thinking type question. How should you put a fuse in a circuit? Okay, I'll give you guys a couple of options. I want you guys to think, which one looks like the correct one? Okay. So we start with, here, let's do a couple of schematic diagrams. I have a voltage source, maybe like an outlet on a wall, maybe it's like 120 volts. I plug something in a wall, 120 volts there. And then, I'll even label that, why not? Make it a little bit more realistic, 120 volts. Then I'll have like some bulb over here, like some number of ohms, or maybe we're plugging lots of appliances. Okay. And then I need to insert a fuse. Here's a symbol for a fuse, looks like this. Okay. Could do that, or I could do that. Right. So this top one would be in series. This bottom one, it's inserted in parallel. Now, what makes more sense for a fuse to work? And remember the purpose of a fuse, right? If there's too much current being drawn, right? Let's say you stick something in a socket and maybe the current's going through you, and it's like a rush of current, and that needs to stop, right? Well, good thing we got a fuse to stop that current, to break that current, right? Now, which one of these is actually going to do that? The top picture in series or the bottom picture in parallel? Because that is the last question you guys are getting right here. And I'm about to find out who my critical thinkers are. Let's find out. Last question for the win, Fuse or circuit breaker is usually inserted. Okay, parallel, true or false? That's like that bottom picture. True or false? All right, most you got it. Woohoo! Most people got it. Oh yeah. All right. Before we go to the winner's podium, let me flip over and show you guys why based on the pictures I just drew. Right. So the statement was this bottom picture, and the answer was false. Right? Because look what happens. Let's say there's a bunch of current going around. If this fuse blows, knock out the fuse. Doesn't the current just keep flowing? Yes. So the fuse is completely pointless in parallel. Versus in series, if the fuse blows here, doesn't that open the circuit and now the current stops flowing? Yeah, that's the one you want. You want the series setup, not the parallel. Okay, makes sense. All right, let's check out who are our Kahoot winners. Do the podium. Here we go. With a bronze, Bridget. Bridget. With the silver, Israel. And with the gold, Bella. Oh yeah. Runners up, Neil and Kaylee. All right, nice job, guys. Nice job. All right, so we got a few minutes left. if you have not turned on that circuit to Kirchhoff table page yet, if you have any questions on that, then that would be a great thing to do here in the last few minutes.